Section 6.5 is continuing this idea with quadrilaterals. Sorry, guys. We've been talking about parallelograms, but today we're going to learn about some quadrilaterals that actually are not considered parallelograms. Now, the title actually is involving trapezoids and also kites, so I left that off on accident, so we're going to put that in there. So we're going to talk about the two remaining quadrilaterals out there. Trapezoids, you're probably already familiar with. A kite, you probably are too. Imagine like flying a kite, what that looks like. But both of these are quadrilaterals.
And I have students that every year say, a kite is really the name of the figure, and it really is. That is the true mathematical name is called a kite.
Now, by definition, we're going to first start with a trapezoid, and then we'll move on to kites. And we'll talk about the definition. We'll talk about some theorems involving them. And remember, don't limit yourself just to the definition. Remember about the theorems involving these things as well. All right, so what is a trapezoid? A trapezoid obviously is a quadrilateral. It says with exactly one pair of parallel sides. So right away, hopefully you know why this is not a parallelogram.
Right, because parallelograms had two sets of parallel sides.
So in this picture, if I told you segment DC was parallel to segment AB, that would make this a trapezoid. Okay. You can kind of look at the picture. You obviously can tell AD and CB won't intersect, but that's something that we'll often have to prove in a sense. Okay, so some vocab to involve a trapezoid. All right, so the bases, notice those are the parallel sides. So what would the bases of this trapezoid be?
So in this case, DC, that segment, and segment AB.
So notice the parallel sides are the bases. And that's something you need to understand, especially when we get to dealing with area at the end of this chapter.
Right.
Okay, the base angles, it says there are two pairs. So a pair has two angles, but two pairs means in each pair, okay, there are two angles. So when you're talking about two pairs of angles, whose common side is the base of the trapezoid.
Okay, so I'm looking at the base AB.
Okay.
That would mean that angle A and angle B would be a set of base angles.
So that would be one pair.
That'd be one pair. And the other pair goes off of the other base. So the other base is the piece that's parallel to it, that segment DC. So angle D and angle C are also a pair of base angles.
Yeah. And
so really it almost looks like all the angles are listed, but they have to be listed with their pair.
Exactly. And you've heard this word base angles before with what kind of figure?
When we talked about isosceles trapezoids.
So just
or isosceles triangles, sorry.
Isosceles triangles. Remember that idea because we're going to actually talk about an isosceles trapezoid in just a minute. Okay, so the base angles basically share that common side, that's the base. Right now, the legs are the non-parallel sides. So what would be the legs in this picture?
So like segment AD and segment CB would be the legs.
And something that we've talked about, again, referencing this triangle idea, we've talked about legs of a triangle before.
Sure.
Obviously, trapezoids and triangles are not the same thing, but there are some characteristics that they have in common. Okay. Now, the last vocab on this slide is when a trapezoid is an isosceles, that means the legs are congruent. Kind of makes sense, right?
Sure, because in isosceles triangle, the legs were congruent, so isosceles trapezoid, legs are congruent.
So there's where they have in common. Now, does that mean all trapezoids are going to be isosceles?
No.
No, but when they are, there's some cool things that happen with it, okay? So if segment AD and segment BC are congruent, there's some things that we'll know on top of that. So let's learn about those things.
All right, so we're going to talk about some theorems. And notice this says if a trapezoid is isosceles. So here we're going to be starting off knowing that this is an isosceles trapezoid. Now, just by definition, what does that mean?
Okay,
what do I know about?
Trapezoid means we only have one pair of parallel sides. So let's say segment AB and segment DC are parallel.
Okay.
And isosceles means the non-parallel, the legs are congruent. So segment AD and segment BC are congruent.
Perfect.
So you have to know that before you can even use this theorem.
Exactly, because this is part of our given. If we know that this is the case, then what we can conclude is that each pair of base angles are congruent.
Okay.
So now let's think about the pairs of base angles because we can identify them, but now this theorem is telling us that if we know it's an isosceles trapezoid, and it has to be isosceles, that's the key word. Not just any trapezoid, but an isosceles trapezoid, then the pairs of base angles are congruent.
So that means angle D would be congruent to angle C because those are base angle pair, and then also angle A is going to be congruent to angle B. So technically, you know two sets of congruent things based on knowing this is an isosceles trapezoid.
Exactly. Really, several sets of congruent things. We know the congruent sets of angles that we have there, the AB and the CD. We also have the segment AD and segment BC that would be congruent as well. So knowing that it's isosceles, and so really you have to have there that AD and BC are congruent first. So you have to know it's isosceles.
Now this time to me kind of sounds like when we talked about isosceles triangles, that their base angles were congruent.
Yeah, that base angle theorem.
Very similar to that.
Very similar.
Now, notice it doesn't have a name. We're not going to call this the base angle theorem because this is not dealing with triangles. So just when you're using this, you're going to have to explain it more, which is no big deal. Okay, this is more, we're going to apply this more than use it in a proof. All right, now another theorem involving a trapezoid, it says if a trapezoid, okay, so we have a trapezoid, which basically means what?
That segment AB and DC were parallel.
So we have to know we have one pair of parallel sides. And it says it has a pair of congruent base angles. So, for example, what could be congruent in this picture?
So, like maybe angle D and angle C were congruent.
Now, could you have said angle
A and B?
Yeah. So it really doesn't matter. It's as long as you have one pair. So let's say I stated angle A is congruent to angle B.
Yeah.
Either way, as long as you have one pair, it says a pair, then it says it's going to be isosceles.
Oh, okay.
So what is that going to basically mean?
It almost is kind of like the converse of our last theorem, except for here I only need one pair. All right. So that means that segment AD and segment BC are congruent.
Now, if you know then this is isosceles, then wouldn't that mean the other base angle pairs would be congruent?
Right.
So you could kind of then go back to that last theorem and kind of go off of that.
Okay.
So these two theorems, I like how Ms. Hooker said it. They're very much, this one sounds like the converse of the last. It's a little bit different, but it's very similar to that. Okay, notice the two theorems we've learned so far all involve something about an isosceles trapezoid.
Yes.
Okay, so keep that in the back of your mind.
All right, this next theorem says if a trapezoid is, again, isosceles, so we have to know we have an isosceles trapezoid. Again, that's a big thing right now. Isosceles trapezoids. That's when we have a lot of cool things that happen. Regular trapezoids, there's not as many neat relationships. But if you have an isosceles trapezoid, and then it says if and only if. Ooh, what does that mean?
You can interpret it forwards and backwards.
Yeah,
so it's a biconditional.
It's a biconditional statement. So if we've got a trapezoid that's isosceles, then we know that the diagonals are congruent. But I could also work that backwards and say, if you have diagonals that are congruent, then we know that it's what?
An isosceles trapezoid. Wouldn't you have to know first?
You'd have to know it's a trapezoid, yeah.
So you know that the diagonals in a trapezoid are congruent, then you know it's isosceles.
Right. Because if you just knew you had diagonals that were congruent, it could be a what?
It could be a rectangle.
Could be a rectangle,
It could be a square.
Right.
Yeah.
So here's the key. We want to talk about if we know that this is an isosceles trapezoid. So what would I need to know if I know that it's an isosceles trapezoid?
If you know it's isosceles, well, you have to know it's a trapezoid first.
Okay, let's start with
either
that.
way, so we have to know segment AB is parallel to segment DC.
And really, here's the thing, guys. You need to know that either way.
Yeah.
You need to know you have one set of parallel sides. So we need to know that AB is parallel to DC. And
Before
then
you can do anything.
Before you can do anything. Then you can say, if we know then that AD was congruent
to BC.
Then what do we know?
Then you could say segment AC is congruent to segment BD, which are the two diagonals.
Exactly. Or, to work it backwards, if I knew that the diagonals were congruent, so if segment AC is congruent to
BD, then you can say segment AD is congruent to BC. But I like that what she wrote off to the side. You need to know first that there is a trapezoid. Okay, so none of these theorems involve other types of quadrilaterals. And that's where I find students get struggle, especially now that we're throwing in 2 more quadrilaterals out there. So when you are asked to prove something, especially when we get to a coordinate plane, you have to kind of first narrow down what kind of quadrilateral are you dealing with first, right? Is it a trapezoid? Is it a parallelogram? So there's things that you're going to have to do that. Okay. Let's try to apply this now.
Okay.
So first of all, okay, it says fine. We got a bunch of measures to find. But what do you notice in the picture? What are we dealing with?
Okay. As I look at that picture, I see that we do have a trapezoid because we have one set of parallel sides.
Okay.
And we actually have an isosceles trapezoid because we also can see that CF, segment CF, is congruent to segment DE.
All right. So we know we can narrow that down. So we're going to be thinking about all those things we know about isosceles trapezoid, which there's quite a bit.
Yeah. And really, I'm not going to be using definition because definition is just what's already listed in the picture. Okay, so let's think about the properties.
All right, so we're trying to, and one thing, notice they do have something off to the side. They say CE is 10, so you might even draw that in. Notice CE is actually a diagonal. So probably trying to know something about diagonals of an isosceles trapezoid. All right, let's start with DF. Well,
well, DF is that other diagonal. So we know that the diagonals in isosceles trapezoid are congruent. So I know that that's 10.
So if you had to explain it, I love what you said. Diagonals are congruent in an isosceles trapezoid.
Yes.
All right, moving on. Angle C's measure. So this guy right here. This is the one we're trying to find.
Well, I remember that the base angles are congruent.
I'm going to get rid of this diagonal. Whoops. That's not what I wanted. Where's the... All right.
All right. I know that base angles are congruent. So I'm just going to fill in because I still don't know really anything about angle C, which is where I'm going.
So, but C we know is congruent to
D.
So if you know angle D, you could find angle C, right?
Exactly. But I'm going to start at part D, down at the bottom where it says angle F. I know that that has to be 96.
Okay. So you could kind of move around. You don't have to go in this order because angle F is going to be the same as angle E.
Right. So I would start there if it was me. And then I still don't know what this angle C and angle D are, but I do know that all of the angles of any quadrilateral equal 360 degrees.
Okay.
So if I took my 360 minus my 96 and minus another 96, that's going to leave me with 168. Now, that right there is both angles C and D together. So I need to divide that by 2 because I know they're congruent.
Okay.
And when I do that, I know that that would leave each one to be 84.
So that would make angle C 84 degrees.
And angle D.
Angle D.
Yeah.
Now, do you see another way you could find angle C and angle D? Because I like how Ms. Hochgravy did this because I think most people approach it this way. But here's the downfall to that. If this is not an isosceles trapezoid, okay, and they ask you to find angles that are not considered your base angles, you can't use this approach because not in just a regular trapezoid, or not regular, like if I give you a trapezoid like this, right, obviously these are not isosceles.
So the base angles aren't congruent.
Yeah, so how could we find angle C? Let's focus on that. How could we find angle C if I do know one of the other base angles?
Well, I do see that I've got some parallel lines. Could I use some of those ideas that we learned about parallel lines?
If these are parallel and we have a transversal.
Oh, they're consecutive interior angles. They're going to be supplementary.
So that means angle F and angle C are supplementary, as well as angle D and angle E. That's really helpful.
That is helpful.
So not only do we know that the base angles are congruent in an isosceles, but in any trapezoid, the consecutive angles, now not all the consecutive, like angle C and angle D are not necessarily.
The ones that are not base angles with each other, basically.
Exactly. So angle C and angle F, so in this case angle C and angle F, and angle D and angle E, these are supplementary to each other. Okay, so to find angle C, you could do 180 minus 96, which would still get you to 84.
Okay.
I know for a fact there's a question on your classwork that involves this. So we want to make sure that we're thinking not just about, okay, this is an isosceles trapezoid. What does trapezoid really mean? Okay. So keep that in the back of your mind.
All right. Here we go. We've got a coordinate plane.
Yes.
And it says that we have the vertices, W, X, Y, Z. And I've given you those points. We're supposed to show that it is a trapezoid. And the question then says, is it isosceles?
Okay, so does that mean I could just graph it like I have here and just say that's I've shown it? It's a trapezoid?
No. Showing means I want to see your work. Not just a picture to where we can maybe make assumptions. We want to show using some more.
So we're kind of proving it, but more with coordinate notation. So I'm thinking back to even the last few or couple sections when I showed it was a parallelogram or found out if it was a rectangle or whatever, I had to use the slope and distance formulas.
Exactly.
Okay.
Good thought.
So if I'm trying to show it's a trapezoid, By definition, that means you only have one pair of opposite sides that are parallel.
Uh-huh.
So if I can show I only have one pair of opposite sides that are parallel, that means I've shown it's a trapezoid.
Perfect.
Okay.
Okay, so let's do that.
So how do I show that parallel? That means finding the slope.
Okay.
So we drew a sketch to kind of give you an idea of which sides would be non-consecutive or opposite type things.
And guys, you don't have to have the picture on a coordinate plane. If this was me on my paper, I would just say, okay, I know I'm looking for some kind of a trapezoid. I don't know that that's drawn to scale. I don't know if I've even listed which ones are the parallel sets based off of this. But then just go around and list W, X, Y, and Z and say, okay, well, I know which ones are opposite sides now.
Yeah. And
That's
here's
all
the
we're
deal.
really
You may
looking
not draw it, like Ms. Hogray said, to scale. So really what you have to do, and even if you draw it in the coordinate plane, you still have to find the slope of all four sides.
Right.
Because if you just show that one pair is opposite sides are parallel, how do you know if you don't know about the other pair?
Yeah, because it could be a parallelogram.
So I'm going to find the slope, let's say, of WX. Okay, and WX, so it would be 0 minus 2 over 3 minus a negative 1, so plus 1. So that'd be a negative 2 over 4, so negative 1/2.
Okay.
Okay, and the opposite side of that, so the slope of ZY, that would be a 1 minus a negative 3, so plus 3, and negative 4 minus 4.
Okay.
So 4 over negative 8, which is also a negative 1/2. So if some of you are thinking, well, all right, I've shown that those two sides are parallel, okay, but that still hasn't really shown it's a trapezoid. We've only shown one pair of parallel sides, but by definition, it says exactly one. So we have to show the other two sides are not parallel.
Right.
So let's do the slope of WX. Or WZ, sorry. WZ. And WZ would be 1 minus 2 over negative 4 plus 1. So a negative 1 over negative 3, which is a 1/3. And then XY slope, okay, be negative 3 minus 0 and 4 minus 3. So it would be a negative 3 over 1, which is a negative 3. Okay, so those are obviously not parallel.
Right. Which is good, because we were trying to show that it is, oops, sorry, not parallel, that it is a trapezoid. They already told us it was. We're just trying to show that.
Okay, so I've done that. I've shown that it is a trapezoid. Now the next part says we need to decide if it's an isosceles trapezoid. So here's what I'm thinking. We've learned several theorems involving trapezoids, involving isosceles to be exact, but all of them involve the fact that you have to know it's a trapezoid first. So we've done that. Now, the couple things I think about is, well, base angles are congruent. Well, we can't really show congruent angles
from a coordinate
plane. So the other thing is we could just find if the legs are congruent.
Okay.
Or we could decide if the diagonals are congruent.
Exactly.
So you have two different approaches here.
And either way, you're going to be using two distance formulas. So it won't really matter to us which approach you use. Which one do you want to do today?
Let's do the legs.
Okay.
Let's do that. So we're going to decide the legs are the basically parallel sides. So WZ.
Right. So we're going to take the square root of.
So WZ. So it'd be a negative 1 plus 4 squared. And then 2 minus 1 squared. And that gets you what? 3 squared is 9 plus 1 equals a radical 10. And we're just going to leave it like that.
Sure, because we just want to show that they're the same. Okay?
If they are. We don't know if
well,
they
yeah.
are.
That's true.
It just says, is it? So we're really, the question is, we're trying to figure out if it is or not.
Okay.
So XY is going to be 3 minus 4, that quantity squared, plus 0 plus 3, quantity squared. So that's going to be 1 plus 9, so square root of radical 10. So is the trapezoid, or is that trapezoid isosceles? I'm going to say yes.
Okay, now what if I said explain?
I would say my explanation would be because it is isosceles because the legs are congruent.
Right. So just kind of be prepared to, if we say, is it isosceles trapezoid, know why it is.
Yeah.
So that you can say either the legs were congruent, you could have found the diagonals were congruent, either way.
And
they should.
Yeah. If it ends up being isosceles one way, it's going to be isosceles the other.
Exactly.
All right. One more concept involving trapezoid. There's a lot more with trapezoid. Kite is more limited, right? We've seen this word mid-segment before. Where have we seen it?
Oh, with triangles.
Yeah. So you've noticed some similarities with trapezoids and triangles with some of the vocabulary. A mid-segment of trapezoid has some similarities too with a mid-segment of triangle. Notice it's a segment, and it connects the midpoints of its legs. Okay? A mid-segment of triangle connected the midpoints of any side. But we have to be more specific here. So in a trapezoid, there's actually only one mid-segment.
Okay.
Now, first of all, we have to know it's a trapezoid, so let me label this to make sure it's precise here. Now, it says connect the midpoints of his legs. So what are the legs of this trapezoid?
Okay, the legs were the non-parallel pieces. So AD and BC were the legs.
So if I find the midpoint of each of those sides, and it doesn't have to be isosceles, and we purposely drew one that wasn't, and if I connect that, if I connect those midpoints, that is the mid-segment.
Okay. But I like how you said there's just one with a trapezoid.
So if I call this like M and N, so segment MN is your mid-segment. And there's only going to be one. Maybe make a little note of that. Only one in a trapezoid.
All right.
Now, there is a theorem that goes along with it, of course.
And it's going to sound a little familiar. Okay. It says the mid-segment of a trapezoid is parallel to each base and half the length, or half the total of the sum of the lengths of the bases. So do you remember when we talked about with the triangle?
Yes, in a triangle, the mid-segment was always parallel to the opposite side.
Right.
Well, in this case, being a trapezoid, it's going to be parallel. If it's going to be parallel to one base, it's got to be parallel to the other.
Exactly. The difference, a triangle ended with a point, right? So you can't say it's parallel to a point. But we still said it was parallel to it, to that third base. So now it's just parallel to both bases. And we said it was half as long as the one base in a triangle. Well, here's the deal. I'm not just ending at a point. I'm ending in another flat piece.
So you have two bases.
We have two bases. So we're going to average those two bases. Is essentially
good word. Good word.
So, yeah, when we say it's half of the sum, we're averaging them. So if I don't know, how do you want to write this?
Let's say, okay, so NM is parallel. Let's say that segment is parallel to segment AB, and it's parallel to segment DC. So all of those segments, let's put segment bars, all those segments are parallel. And the other part of this theorem, which is the one that you're going to use mostly, the length of NM,
length
is equal to, now, there's a couple ways you can do this. Half, so 1/2, the sum of, which means I need to put it in parentheses, of AB, that length plus DC's. Because you're adding those two bases and taking half. Now, another way of taking half is the same thing as dividing by 2. So you could add those two bases and then divide everything by 2.
So you're just averaging the bases. If you think about it, that length should be an average of the other two lengths.
Yeah, because it's made up of the two midpoints of those legs.
Exactly.
Okay, so this theorem is something that it's not completely out there. I think you see connection from triangles.
Yes, and again, this is not just isosceles trapezoids either. This works for any trapezoid.
Yes, very good. All right, so it says, how long must segment AB be to ensure that it divides the legs of this trapezoid in half?
Okay,
all right?
So it sounds like we're trying to say that it is a mid-segment.
Yes.
Because if it's dividing the legs in half, then we're saying that we know that those are the midpoints.
So in other words, we're trying to make this happen. And the only way that's going to happen is what's got to be true about this mid-segment. So we're basically saying that segment AB has to be a mid-segment. So what do we know about segment AB?
Well, we know that it is, it's the average of the other two bases.
Okay. So that means I could say the length of AB, which is
7x plus 2, is equal to, and I'm going to write it as 1/2 of the quantity of 6 plus 8x plus 13. Okay. Now, I don't really love working with halves.
Okay.
So I'm going to go ahead and clear the fraction.
Okay.
So let's go ahead and let's multiply everything here by 2, which is going to make it a 14x.
Now, when you multiply everything by 2, you're basically multiplying this by 2
yes,
and this by 2. You can't multiply inside.
Right, because when you multiply that side by 2 and multiply that half by 2, it's just going to get distributed as I take care of that anyway. Okay, so I'm going to go ahead and say that that's going to be a 14x plus 8. Sorry, 4. Where am I even? I don't know. 14x plus 4 is equal to, and half of the 2 is going to give you just a 1.
Okay.
And 1 times the quantity is not going to change it. So it's just going to be a 6 plus 8x plus 13. And then from there, I can start combining some like terms. And I know that's going to give me an 8x plus, oh, sorry, you're moving it. Okay, there you go. And then as you solve for the x, we're going to be left with a 6x equals 15. And x is 5 halves if we'd simplify 15 sixths.
Now, the question says, how long must segment AB be?
Okay, so I haven't really found that yet because I've just found out what x is. But AB is 7 times that 5 halves plus 2. So let's see, 7 times 5 halves would be 17 and a half plus 2 would be 19 and a half.
So if I put 19.5, would you be okay with that?
Sure.
Yeah, because it's exact. You want to leave it in fraction form if it's not an exact fraction. And again, guys, if taking a half of a sum, it's the same thing as dividing. So you could have written it as the 6 plus 8x plus 13 all over 2 is equal to that mid-segment.
In fact, if you write it that way, you could put 7x plus 2 over 1 and make a proportion out of it all.
Or you could just say, okay, multiply each side by 2, kind of like what Ms. Hograby did there. So either way, it's just solving an equation, which you guys know how to do. Okay, so you've answered the question. We're good to go. Let's move on.
All right, we're moving on to our next figure, a kite. This is the last quadrilateral we're going to focus on. And we first are just defining a kite. The kite, it's a quadrilateral that has 2 pairs of consecutive congruent sides. We've talked a lot about opposite sides congruent, different things about some sides possibly being congruent. Here we've got consecutive congruent sides. But the opposite sides are not congruent in a kite.
Well, that's because if they were, it would be a parallelogram.
Exactly.
And there nowhere does it say a kite is a parallelogram. And you guys know that.
So when we're looking at this kite, what are the 2 legs that you think probably we're talking about here being? Because I'm telling you, this is a kite. So what are the 2 legs that look like they're probably talking about the
kites don't have legs, do they?
Sorry, the sides. Thank
you. Okay.
Thank you for correcting my vocabulary. The sides. What sides would we be talking about that would be
okay, so let's say segment AB is congruent to segment BC. So that means segment AB cannot be congruent to CD. So let's say CD has 2 tick marks. And BC cannot be congruent to AD. So that means AD is going to have 2 tick marks because you have to have 2 pairs of consecutive congruent sides.
Right.
And that's what a kite, I mean, when you think of the word kite, I picture that. I mean, I know there's some kind of fancy designs out there, but this is the most basic type of kite that's out there.
Exactly. So when you're looking at this, yes, you're going to have 2 sets of consecutive congruent sides. Opposite sides are not congruent.
So notice this one has nothing to do with parallel. Okay, so if I ever have to, because eventually you're going to, I know in the next section, we're going to be trying to figure out, okay, what kind of quadrilateral it is. So knowing that this is completely different than all the others, that's something that we also want to keep in mind when we're doing it on a coordinate plane. Right now, there are some theorems involving a kite, and notice how it starts. It says, if a quadrilateral is a kite. So you know it's a quadrilateral, so it has 4 sides, and it's a kite. So looking by the picture, I've communicated that. Okay, you have 2 pairs of consecutive congruent sides. Opposite sides are not congruent. It says, then, what do we know? Its diagonals are perpendicular.
Oh, okay. We saw perpendicular diagonals with rhombuses and squares too. So it's not just any time that you have diagonals that are perpendicular, it will be a kite. It's that if it is a kite, this is also true.
So if I give you this as a kite, then what can we say?
That segment BD is perpendicular to segment AC.
So we can say those are perpendicular here. Okay? Now, again, this doesn't prove it's a kite. All right? And I'm going to just stress something before we move on, is that really the only way to show it's a kite is by its definition. All of these theorems are going to say if you have a kite, then what do you know? The diagonals are perpendicular also involve the diagonals are perpendicular also involve rhombuses and squares. So we don't want to limit that idea. All right, now another theorem involving a kite. Notice again, it starts the same way. We have a quadrilateral, a kite, then exactly one pair. All right, we've seen this idea with a trapezoid, exactly one pair, but this is saying the opposite angles are congruent. So only one pair of opposite angles are congruent. Now,
Okay.
how are we going to know which ones are going to be congruent?
Well, I see something that I think this helps my students every year too. If you drew in diagonal AC, notice that we've got two congruent triangles.
Yeah, because AC is congruent to itself.
Exactly. And if you see that diagonal that makes those two congruent triangles, sometimes that helps to realize then, oh, all those corresponding parts are congruent. So we know that angle B is congruent to angle D. And I think that's just a good visual of it. Now, another way to keep in mind, it's the included side between the non-congruent legs.
Yeah.
But I think it's easier to see the visual of that on this
But I like that. I like that you had me draw that in. So in a kite, the opposite angles that are congruent are always the ones that are basically formed by the non-congruent sides.
Right.
It's the included angle between it. The other angles, angle A and angle C, there's no way those can be congruent as well, because then what kind of figure would this be?
A parallelogram.
Yeah. So none of these characteristics, remember, are kind of shared necessarily where they're going to be able to prove it's a kite.
Okay. All right, so now I'm telling you that this is a kite. We're supposed to find HK. So what do you notice about HK?
Well, HK is a diagonal.
And what do you know about diagonals within a kite?
Well, in a kite, and I like that you said that, because if we're finding something about HK, which is diagonal, we're probably dealing with the diagonals of a kite. Diagonals are perpendicular.
Okay, so that only gives me an angle. It doesn't really help me with sides. But
Okay.
I see if I've got some other known pieces, what do you notice that we have here?
Well, the other pieces that are given to us are involved with, it says, so a square root of 29 is part of GH, and the 5 is part of GP, and then HP, which is part of HK, forms a right triangle together. So I'm thinking, this is what I'm thinking. If I can find HP, then maybe I could find HK. And I'll kind of explain what I'm thinking once I find it.
Okay.
So let's go ahead and find HP. And we're going to use the Pythagorean theorem because we have two sides of a right triangle. So let's do 5 squared plus, and you did x, so x squared, that's your HP, equals radical 29 squared. And again, guys, if you're using x, make sure you know what x represents.
Right,
Like,
and I wrote that on here just so we don't have to write out HP every time. But mark it on your picture so you know what you're finding.
Because otherwise you end and you think, oh, I got X, I found the answer. But that only represents HP. All right, so that's 25 plus X squared is equal to 29. Square root of 29, or the square root of 29 squared is just 29.
Right.
So I get X squared is equal to 4. So X is technically plus or minus 4 or 2. But since we're dealing with lengths, we're only going to deal with the positive amount.
Okay, so we know that this right here is 2. So HP is 2.
Okay, so here's what I'm thinking. I'm thinking, because this is a kite, segment GH and segment GK are congruent. And I know those are right angles. And I know they share GP, which means those triangles GPH and GPK are congruent because of HL.
Right.
Which means their corresponding parts, HP and PK, are going to be congruent, which means PK is also 2, which means HK is 4. Now, I'm assuming some of you are thinking that in advance, right? However, there's no theorem that supports, there's no theorem that we learned that diagonals bisect each other, because technically
they don't bisect each other.
There's only one that's bisected.
One is bisected, though, and it will always be bisected. And really, you've just kind of done a proof of that. We just don't have a theorem named that, or that helps us to find that otherwise.
Okay, so it says find angle S, the measure of angle R, the measure of angle T. So this time we're dealing with still a kite, right? And we're dealing with the angle. So let's refresh our memory. What do we know about the angles of a kite?
Okay, I know that within a kite, there's one pair of
So which ones would that be?
So I know that in a kite, one pair of opposite angles are congruent.
So which ones would that be?
That would be the angle S and angle U, because I know that those are formed by the two non-congruent legs. Or not congruent sides, yes. I keep wanting to say legs.
We've been talking
legs.
about,
I know. So those are going to be the two congruent angles. So measure of angle S is 125 degrees.
Okay, I went ahead and wrote that down. We got 1 down, 2 to go.
Okay, now, we don't know that in fact, we know the other two angles are not congruent.
Exactly.
But that's about as far as we can go with that. So I think probably from here, I'm going to go ahead and go to the idea of a quadrilateral. All the angles together equal 360 degrees. So let's say that our x plus 30 plus the other x that we have over here.
Oops.
Plus the 125 plus another 125.
I'm going to go back here.
Okay.
Couldn't squeeze that in. So basically 2 of the 125s.
Right. Will equal our 360.
So we go ahead and solve it. Let's just
and x would end up being 40.
Now, well, that will help you find both of the remaining angles, right?
Right, because we know that the measure of angle T was just x. So the measure of angle T is 40. Good idea. And the measure of angle R would be that 40 plus 30, so we'd be talking about 70 degrees.
And to double check, you could make sure all 4 angles add up to 180 or 360.
Yes.
I do that as well. Some of you might have found you've done that. All right, we have one more example.
Okay. And this says determine if the given points represent the vertices of a kite. So do we know that it represents a kite?
No, it says determine whether it is. So we're trying to decide if it is or not.
And, on a lot of these, we've given you the little picture on the coordinate plane. We didn't even do that here. Mm-hmm. It's not needed, and I wanted you guys to realize that it's not needed. If I just draw in a kite, and I have no idea which angle or which vertices are corresponding with which one of these points here, but I'm just going to go ahead and go around my figure and say A, B, C, D.
Now, I want to stress that we don't know it's a kite. So all we know is it's a quadrilateral because it has 4 vertices. We're deciding if it is. So if we think about it, by definition, we have to show that only the consecutive, we have 2 pairs of consecutive congruent sides and the opposite sides are not.
Right. So really, what are we going to have to be doing?
Using the distance formula.
The distance formula. And how many distance formulas are we going to find?
All 4 sides.
Right. So let's start with which one?
AB.
Okay.
And we know AB, so we'll do -3 minus 0 squared plus 6 minus 9 squared. So that's going to be 9 plus 9 is equal to square root of 18. Okay, now we don't really know we know that consecutive, we just don't know, we don't know if it's a kite. So let's say I find AD next.
Okay.
And AD is going to be the -3 minus 0 quantity squared plus 6 plus 10 squared. So that's going to be 9 plus what?
16?
No, but square 16,
and
that's
square,
256, right?
Yeah.
And that's going to be the square root of 265. Now, right away, those two are obviously not congruent.
Right.
But that doesn't prove anything.
That just proves that those would not be the congruent consecutive sides if that was a kite. Okay.
All right, so let's do BC. I'm going to go to the other consecutive.
So then this might possibly.
We'll
find out. Okay.
BC. So 0 minus 3 squared plus 9 minus 6 squared. So that's going to be square root of 9 plus 9, which is the square root of 18.
Okay, so right now I do see that
BC.
AB and BC are congruent.
So we might even label that in their picture so we can kind of get a visual of the picture. So here's the deal. We've only shown 1 pair of consecutive congruent sides. So have we determined if this is a kite or not?
Nope, not yet.
No. All right, so we have one more side. CD is the last one. So square root 3 minus 0 squared plus 6 plus 10 squared. So that's going to be the square root of 9 plus 256.
Oh, yeah, I keep on right 16. 256.
Which is the square root of 265, which is the same as AD. So AD is congruent to CD's length. Okay, so here's what I'm thinking. I am thinking it is a kite.
And why?
There are two pairs of consecutive congruent sides, and opposite sides aren't congruent.
Perfect.